Hey everyone, welcome back to another Calculus 2 lesson. Today we're going to talk about volume, but in a very different sense. Not volume created by revolutions around an axis, but volume is created in a different way. Let's illustrate this by way of an example. Suppose we have a base of a solid bound by three curves, F, G, and the vertical line, x equals 0, the y-axis. And let's further suppose that all the perpendicular cross-sections, namely perpendicular to the x-axis, these cross-sections are all equilateral triangles. Any way we slice this solid perpendicular to the x-axis, we will see an equilateral triangle. So find the volume of the solid. Well, here's the picture. F is that downward sloping, negatively sloped line. G is there. There's my x-axis, y-axis. Intercept of F and G is at x equals 2, which you can get by saying they're equal. Now what's happening at the base level? What does this base look like? Well, let's take a closer look. So there's my F, negatively sloped. There's my G, positive slope. And G is just F times negative 1. So there's a nice symmetry here. My x-intercept of 2. And now, how do I create the solid from the base? Let's just pick this two-dimensional region. How do I create the solid shown on the left? Well, I do the following. I draw infinitely many perpendicular line segments, perpendicular to the x-axis, in my region, and I make a commitment. I make a commitment that every single one of those red vertical segments is going to be the base of an equilateral triangle. And with that commitment in place, I automatically generate the solid to the left. The bases are those red things, and they project out. Equilateral triangles project out from those red vertical line segments. So that's how I can visually create that thing, that solid on the left. Every single one of those right vertical line segments is the base of an equilateral triangle, and then each of those triangles are popping out at you. That's the way to visually construct the solid, but how do I go from a visual construction of the solid to mathematically finding its volume? Well, I need a different visual for this. So rather than dealing with infinitely many thin line segments, how about I deal in familiar territory? So here I've drawn 11 rectangles, left endpoint rectangles. Now I'm going to extend them down to G to create bigger rectangles. They're twice as big because of the nice symmetry between F and G. Now from these, I'm going to do something very special, very visual. I'm going to project equilateral triangular solids from each of those 11 rectangles, and boom, voila, look, ooh la la, look at this. This is what I create. I create this solid region in green. And this solid region in green, composed of 11 equilateral triangular solids, is a good approximation of that solid on the left. So the volume of this on the right is a nice approximation of the volume of the solid on the left. Now from this 11 equilateral triangular solid region, I'm going to pick out just any one of them, and I want to derive an expression for its volume. Well, we start in familiar territory. Well, rectangular solid, volume is going to be length times height, or A times H, pi r squared H for the cylinder, A times H. So following the similar pattern here, where A is the area of the base, if I can find an expression for the area of that equilateral triangle, that equilateral base, then V is just AH. There are my sides. My delta X is the height, of course, which we can see by comparing to the picture on the left. There's my delta X, but now I want to derive an expression for the area of an equilateral triangle. That'll give me my A value. I want to do that in terms of S. S is the side of an equilateral triangle. I can divide the triangle up like so, and here's a very nice way to get the area of an equilateral triangle. Split it in half, get a 30-degree angle, do some 30, 60, 90 stuff, and here is my expression for the area of any equilateral triangle. S squared times square root of 3 all over 4. All over 4. So, the volume of the solid is approximately the same as the volume of those 11 equilateral triangular solids added together. Now, I want an expression for S. Well, f of 0 is half of S. And f of 0 I can also express in my familiar Riemann way. I'll let A be equal to 0. I do some left endpoint 1 minus 1 delta x thing. That's the reason for the weird notation you see. So yes, S is 2 times f of 0, i.e. f of A plus 1 minus 1 delta x. V of 11, therefore, is A1 delta x plus A2 delta x. Using that formula at the bottom, A delta x. And so now I just sub in for A1, A2, and all the way up to A11, and I get this. Just left endpoint rectangle stuff, but in a slightly different makeup. So, the exact volume is going to happen when each of those equilateral triangular solid regions gets squeezed to a width of 0, i.e. n goes to infinity. So there we have it. I minus 1 delta x is the way we account for left endpoints. That's the term there. But now I'm going to create a new function. I'm going to say let ax, a of x, be, 2 times f, the whole thing squared, times root 3 over 4. If f is continuous on the interval ab, i.e. 0 to 2 in this case, ax is also continuous because square a continuous function is continuous, multiplied by a scalar, still continuous. So v, we can write that as this. The limit as n goes to infinity of the sum from 1 to n of that guy right there. And the great thing about this is we know this fits the form of a definite integral. In fact, it is a definite integral, and we have a much shorter notation for that boxed here in yellow, integral from a to b of a of x. This is our all-purpose formula for finding the volume of a solid with known cross-sectional areas, known cross-sections. And look, we already have a of x. A of x in this case is 2 times f of x, the whole thing squared, times root squared of 3 over 4. A is 0, b is 2. We throw that into this formula, and we can solve for the volume exactly. So here we are. We can pull out the 4 by squaring 2. 4's cancel. I can also pull out the root 3. Root 3 integral from 0 to 2 of f of x, but f of x was, remember, 1 minus x over 2. Plug him in, square him. Now you can fold this out if you want, but the easiest way to do it would be to u sub u equals 1 minus x over 2, du is 1/2 dx. I multiply by negative 1/2, I need to multiply by negative 2. I bring that negative 2 on out, I get this. I also need to change my bounds. 0 to 2 for x becomes a 1 to 0 for u. And now I can flip that integral to make it a positive 2 root 3 on the outside. And this is a very simple integral giving me this. That is the number of unit cubes you can jam into that solid on the left. Again, cross-section method is very powerful. It's not like revolution. We didn't revolve anything. We just made a commitment to project certain shapes from a given base. Now, just to illustrate how powerful this approach is, let's prove the volume of a sphere. We've done this via revolution. Now let's do it via non-revolution, via cross-sections. There is my semicircle. I'm going to project from these vertical line segments, infinitely many quarter circles. So imagine quarter circles popping out at you to create a quarter sphere, just like what we did for equilateral triangles in the last problem. Now we're doing quarter circles to create a quarter sphere. My a of x here is going to be the area of any one of those infinitely many quarter spheres. Generic representation shown. Of course, the radius, length of those blue segments, is square root of r squared minus x squared. And the area of a quarter circle is 1/4 times pi times the radius squared. That's what I'm doing there. And a of x is that guy at the bottom. To the volume, I use my formula again. A to b is negative r to r in this case. A of x we just solved for. We throw him in. Now we can integrate, and by the way, r squared and x squared are even functions. So negative r to r, I can recommend that as 2 times 0 to r of the integral of 2 times the integral of 0 to r of r squared. Same deal with x squared. Yank those 2's on out, and we get this, 1/2. And I just realized I'm missing a pi, so let's go ahead and put a pi back in those steps. There we go. That bracketed term is 2/3 r cubed. And that is the volume of a quarter sphere. So the volume of a full sphere is going to be 4 times that guy, and voila, ladies and gents, 4/3 pi r cubed. Very beautiful stuff. Very different from revolutions, but ends up being the same thing. So quite nice, quite nice. But we needed to know the area of a circle. The area of a circle is absolutely needed to prove the area, volume of a sphere. So go ahead and pause the video and try this one. Try to prove the volume of a cone. Same way. Alright, so getting back into it now. Draw an arbitrary segment, the origin, arbitrary length, arbitrary slope. And there we go. Height is r, h, the run is h in this case. Seems a little counterintuitive, but from this 2D region, I'm going to project quarter circles. Again, quarter circles to form a quarter cone. The line, of course, is y equals r over h, x, mx plus b, b is 0, m is r over h in this picture. So, I am going to square the radius. In this case, the radius is rx over h. So I get a nice equation down there, which I'm going to throw into my volume expression just like before. And we get pi r squared h over 12. Again, the same formula we used to prove the volume of a sphere, the same formula we used in the first problem. There's my volume of a quarter cone. I multiply him by 4 and voila, I get the volume of a cone in a different way. Very different from revolutions, but very powerful. Cross sections are deceptively powerful. You wouldn't think that they'd be so useful, but they are. Many useful things in math are surprising.